we have an induction question over here, and we're asked to show this relationship at the bottom. And you want to show that, importantly, making sure you always pay attention to this, for all positive integers n. So let's take a look at this question where we're going to apply mathematical induction techniques, which your general steps, of course, are going to be prove for n equals your initial case, which in this case is 1. And then you make your assumption for n equals k, where k is an integer greater than or equal to 1, and use that assumption to prove true for n equals k plus 1. And then your conclusion. So basically, that's the outline of our steps. So let's take a look at the case of n equals 1. Should be pretty straightforward. The left-hand side is going to be 3 over 1 times 1 plus 1 times 2 to the power of 1. And that's your first term. You only got the first term. And that's going to be 3 over 1 times 4, which is 3/4. The right-hand side is going to equal 1 minus 1 over 1 plus 1 times 2 to the power of 1. So it's going to be 1 minus 1/4, which is 3/4. So we can show that it's true for n equals 1. So let's now get rid of that, so we have a bit more space. What we're trying to prove is 3 over 1 times 2 times 2 to the power of 1 plus 4 over 2 times 3 times 2 squared plus dot 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 plus n plus 1 over n plus 1 2 to the power of n equals 1 minus 1 over n plus 1 2 to the power of n. Now we've already done true for n equals 1 plus 1. That's done. So what we need to do now is assume true for n equals k. Now remember, you brought in this new letter k, so you need to actually define what this k is. So k is a positive integer greater than or equal to 1, or if you're comfortable, you can use symbols like that. So what we're assuming to be true, and remember we don't actually know if it's true or not, is that we're saying this. So we're assuming this is true. It's important to recognize we don't actually know if it's true or not at this point in time. We're just assuming it's true. And we now need to prove that it's true for k plus 1, which means you still have everything before. But since you've got k plus 1, then k plus 1 plus 2 is just k plus 3. I'll do a bit of simplification here. K becomes k plus 1. K plus 1 plus 1 is k plus 2. This will be 2 to the k plus 1. So hopefully that's all quite clear there. And it'll be 1 minus 1 over k plus 1 becomes k plus 2. And 2 to the k plus 1, because k becomes k plus 1. So that's what we now need to show. And this is basically where all your work in your induction needs to come from. And we'll just give ourselves a bit more space. But it's good to have all these things written out, just so you know where you're heading. Now, I would also recommend that if you're comfortable with sigma notation, which you might not be, but if you are comfortable with sigma notation, then you could use sigma notation to kind of cut down on the amount of writing you need. But if not, make sure you just write everything out to make sure you really get what's going on. Sigma notation is meant to make things easier for you, not harder for you, to sort of make sure you have everything written in a compact manner. But if it confuses you, then just write everything out. So let's start with the left-hand side, which is basically just a copy of this. So to save myself space, I won't copy that out. So left-hand side equals, copy the whole thing. But I'm going to recognize that it's equal to this aspect that I just bracketed in blue plus this one. So it's going to equal a blue bracket with all my terms plus my k plus 3 over k plus 1, k plus 2, 2 to the k plus 1. And the reason I care about that blue bracket is because it is direct match to what I've bordered in green, which is my assumption. Remember, you must always, without fail, use your assumption in an induction question. So recognizing that the blue bracket, which is the first k terms, is equal to the left-hand side of my assumption, I will then replace that with my assumption. I'll do it in blue for now, so it's clear. So that's all of those terms have now been replaced with this part. And you can even write a comment saying using induction hypothesis. And in any induction, you must do that. I cannot stress that enough. You can, of course, maybe perhaps prove a question without using the induction hypothesis, but then you're not doing induction. If you're doing induction, you must use your assumption without fail. So our job now is to basically use our algebra skills to get it to look like this. So since I want a 1 minus, I'll keep the 1 minus. I'll keep it. I won't touch it. Now, I want to get it into one fraction, so I'll basically try to get these things into one fraction. I notice that I've got a 2 to the k plus 1, so I want to keep that. I've got a k plus 2. What is that? Actually, that was a k plus 2, I believe. Yes, that's a k plus 2. So I've got a k plus 2. I'll keep that. So keep in mind what you have and what you don't want to change. So I want to get rid of the k plus 1. I want to somehow get this to that. And so let's make it happen. So I'm going to have a 1 minus that I'll keep. I'll put that in red, 1 minus. Now, what was a k plus 1 and 2 to the k is not going to stay that way because I want to get it, I want to add that up. So because I have a 2 to the k plus 1, I now need to multiply it by an extra 2. That'll give me the 2 to the k plus 1. And I have a k plus 1, but I don't have a k plus 2, so I need a k plus 2 as well. So my original fraction is now going to have a 2k plus 2 at the top. I'll write that, I guess, in blue, just to make it even more clear. So you can see that I haven't really changed the fraction. 2 and k plus 2 cancel, and it's the same thing as before. And I'm going to add k plus 3 all over k plus 1, k plus 2, 2 to the k plus 1. So you have that. Okay. And then now the denominators are the same because you can see you've got the k plus 1. You've got the k plus 2. You've got 2 to the k times 2, which is 2 to the k plus 1. So you now basically have 1 minus, which we want to keep, two to the k plus 2. And this is where you probably want to be very careful. See, I'll do it this way because it's a very common mistake. So what I can't do, okay, is I can't just do 1 minus 2k plus 2 plus k plus 3. I can't do this. This will be wrong. And you might want to pay close attention to this. Okay? It's a very common mistake. So it's wrong for two reasons. Well, one, because I forgot brackets there, which I obviously should have, but that's not the key point of what I'm really getting at. So here you're trying to put them into all fractions. The denominator is the same, and that is correct. However, what is problematic is the fact that if I'm doing 1 minus a fraction, the negative applies to the entire fraction. And while it is correct to say it's 1 minus 2 times k plus 2, this part is correct. This was originally a plus. If I've got it as a plus, this will, you've now basically, if this was negative, this would be okay. But it's not. It was originally positive. So in other words, let me show this in a few more steps. But basically, you've got it as 1. Let me show it this way. 1 minus 2k plus 2 all over k plus 1, 2 to the k plus 1, k plus 2, plus k plus 3 all over the same denominator that I just won't copy out again, which then means the correct way is 1 plus k plus 3 minus 2 k plus 2 all over k plus 1, k plus 2, 2 to the k plus 1. That would be correct. Okay. When I have the positive outside the fraction, the signs stay the same. Positive k plus 3, negative 2 times k plus 2. But what I want is for a negative in front. I want a minus, which means I now need to put a minus in front of the entire fraction. Which then means, because I'm minusing the entire fraction, like minus is plus, so that's the same thing as above, but because the negative applies to the entire fraction, you can think of it as applying to the entire numerator, which then means that it's going to be negative of k plus 3 and then negative of negative, making that a plus. Okay. And that is probably a very common algebraic mistake when you do this, when you do that. Okay. But it is just algebra. So with that in mind, we'll just now quickly see that 2k plus times 2 times k plus 2 is 2k plus 4, minus k, so it's k, minus 3, so it's going to be k plus 1 in the numerator. So hopefully you can see that that's going to become 1 minus k plus 1 over k plus 1, k plus 2, 2 to the k plus 1. Clearly, the k plus 1 will cancel, leaving you with 1 minus 1 over k plus 2, 2 to the k plus 1, which I believe was the right-hand side, as we expected over here. 1 minus 1 over k plus 2 to the k plus 1, as expected. So you would then write your conclusion. So therefore, if true for n equals k, must also be true for n equals k plus 1, and your conclusion, right? So therefore, true for all n greater than or equal to 1 integers by induction, etc. I'll leave that for you to write out in full. But basically, that's how you do the question. You might want to pay particular attention to mistakes like that, where it's very common.